All right, are you ready for some net change theorem? We got ourselves a big night, and maybe you recognize the name of that song. Wish I could throw out some extra credit for that, but I really can't do that, I guess. But so net change theorem is kind of an interpretation of the first fundamental theorem. And so we're going to kind of put some meaning to it rather than just some raw number crunching. And in a nutshell, the net change theorem, and that's my abbreviation, is we're going to say the integral of a rate of change. Oh, what's wrong with that pen? All right, let's see if we can fire up this pen. Okay, the integral of a rate of change is net change. So the integral of a rate of change is net change. All right, now I think, just to throw out a crystal clear example, let's think about something like this. What if I was integrating v prime? And we'll just say that v prime is the rate at which the volume of something is changing. Maybe you're inflating a balloon. So, and if we integrated from t sub 1 to t sub 2, or from a to b for that matter, you're going to get v of t sub 2 minus v of t sub 1. So what we're saying here today is that the difference of those two numbers is the net change, or the total change of volume of the balloon. So I've kind of cut and pasted our definition here, and it's going to be at the top of the next 6 or 7 slides or so. But just keep reminding ourselves that if we integrate a rate of change, the answer is going to represent the net change of that rate. So let's see, we've got water being pumped into a tank at a certain rate. And here's another thing. Rate is derivative, okay? Let's not lose sight of that. When we say the word rate, we are talking about a derivative. But that doesn't mean that the function has to have like a prime on it. So you'll notice they're just using r of t. And so we can process the idea that that represents a rate of change and it's a derivative of somebody, even though it doesn't have a prime on it. The other thing is that the word rate is always going to be married with the word per. So as soon as you see the word rate, you know that we've got something per something. That's automatically tied together. So we want to know how much water actually got added to the tank between 2 and 6. So I would say that the integral of our rate of change from 2 to 6 is going to represent the total amount of water that was added to the tank. So let's just go ahead and integrate 10 minus t from 2 to 6. And this is going to be a real nice one. Now, here's something. We have not been very strong with our notation yet. We need to tack on our own dt or dx. Anytime you write an integral, we've got to make sure that last component is on there. Now, the integral is going to be 10t minus 1/2 of t squared with bounds of 2 to 6. And if I pump the 6 into there, I'm going to get 60 minus, half of 36 is 18. All right, pump the 2 in there, I'm going to get 20 minus 2. And just a little bit of number crunching here. Let's say I've got 42 minus 18, and that's going to be about 24, I hope. Now, what's the units on that? The units are going to be one of my things I want to emphasize the most throughout the problem. Now, that we started with gallons per minute, so if I've integrated, I've dropped the per minute, and now I'm just working with gallons. So tell yourself, anytime you integrate, we take a denominator away. All right, again, just want to keep telling ourselves the integral of a rate of change is the net change. And we've got a function g here. Again, it doesn't have a prime on it, but it is representing the rate of growth of a population. So it's probably like people per year or people per month, something along those lines. And they want us to write an integral that would represent the increase in population between t equals 2 and t equals 16. Again, they didn't really define t. I don't know if it's years, months, days, what it is. But we can go ahead and set up our integral. Said if we integrate this rate of change within the prescribed time frame, we're going to get, whatever the answer is, that would represent the total amount of increase. And I'm going to put that in there. That's our total increase in people. Okay, once again, we're introducing you to a function. They said after t minutes, a certain chemical is decomposing at a rate of 32 e to the negative t grams per minute. Again, I want you to notice that the word rate is married with the per. Those will always be tied together. During the first 4 minutes, we want to represent the total amount of decomposition that has occurred, and we want to focus on the units as we do so. So I'm going to say, let's integrate this function 32 e to the negative t. Throw on your own dt. Of course, you could slide the 32 out front if you wanted to. That's optional. And during the first 4 minutes, so we're going to say from 0 to 4. And, I tell you what, integrating that would not be bad at all. We know the antiderivative is negative 32 e to the negative t. If you want to do a u sub on that to prove that where the negative comes from, be my guest. Since I never did write out my u sub, I don't need to change the bounds. And, of course, we could plug in the bounds and do the subtraction and work it out. Now, I want to focus on the units. I'm going to get, some number when I'm all done. And the final answer is going to be what? Simply grams. Again, so if you integrate grams per minute, the answer you get is just grams. So I've thrown out a couple definitions here. I've established these functions. I didn't give you an equation to go with them, but I said P of t is some magical function that describes the rate at which water is pouring into a bathtub and is represented in gallons per hour. D of t is another mysterious function that represents the rate at which water is draining out of the bathtub. So you've got the faucet turned on, water's pouring in, but then maybe the plug at the bottom wasn't fully engaged or something. So I'm going to throw out a few integrals and you tell me what they describe. If I gave you the integral from 0 to 6 p of t dt, what is that integral measuring? Okay, that's really what I want to focus on, just being able to interpret and put some meaning to the sucker. So think about that for a moment, and if you need to hit the pause button, feel free to do so. I describe that as the total number of gallons that have entered the bathtub or been poured into the bathtub between t equals 0 and t equals 6 hours. Okay. Notice I focused on the units, and I also focused on the endpoints that were on the integral. Okay. Hey, let's throw another one out there. What if I said I want the integral from 2 to 10 of d of t? How comfortable do you feel is describing this one? Again, focus on the meaning and interpreting it. We would say this is the total what? Total gallons, total number of gallons that have drained out of the bathtub between when? We got slightly different bounds. So we'll say between t equals 2 and t equals 10 hours. Make sure those hours are there. The last integral I want to throw out, I think, is going to challenge you a little bit. What if I did the integral from 0 to 10, and I said, let's do p of t minus d of t? What does this integral represent? So go ahead, pause it, just think about it for a little bit, maybe write down your prediction, and then see if we got the same thing. Well, perhaps if we struggled with this one, don't be afraid to write this as two separate integrals. Think of it as the integral of p minus the integral of d. Maybe that adds a little bit more meaning to it. So what we're really doing is we're calculating the total number of gallons that entered, and then we're subtracting the total number of gallons that have leaked out. So what we're really doing is we're describing the net change in volume, okay, or the total change in volume. Total change, net change, those are kind of interchangeable phrases as far as I'm concerned. Volume, measured in gallons, always incorporate your units, okay, between t equals 0 and t equals 10 hours, okay? So don't be afraid to split those two integrals up if that helps. All right, keep telling yourself the integral of a rate of change measures the curve, or that function's net change. So we said the rate of change of the amount of snow on the roof of a house, and I apologize. I don't want you to. I hate to start thinking about snow prematurely. Hopefully, it's still a few weeks or month before we see it, but I'm afraid our days are numbered. And maybe you're anxiously awaiting it snow. I'm not sure, but I'm not one of those people, to be honest with you. But anyway. So we said rate of change, and that's married together with cubic feet per hour Cubic feet is just a way of measuring volume, okay, similar to gallons or something like that. And it's given by this function. Again, don't expect them to put a prime on that function. You know, they can define it any way they want, and it is the derivative of some unknown function, even though it doesn't have a prime on it. So we want to determine the change in the amount of snow during that time interval. So what I'm going to do is I'm going to integrate my rate of change, just as my theorem says. I'm going to throw my own dt on there, and the bounds are going to be 0 to 5. And evaluating that integral is I'm going to get a number, and that's going to tell me the total number of cubic feet, which represents the total amount of snow that has melted off the roof. Well, we've got ourselves, this is just an outstanding problem. I really like, this is very AP-like, simulates a great free response question, and we'll start to see several of these on our tests and spirals. So we've got this, we're picturing a snowball, and the snowball's melting as the temperature rises. And the table below gives selected values of the rate of change of the radius over the time interval 0 to 24. So we're looking at 24 hours, and they just made notes of how fast the rate was changing at certain times, depending on whether the sun was out or whether the clouds were out, whatever. So they want us to, using correct units, we want to explain the meaning of this integral right here. Now remember, R of t is a rate of change, and it's measured in millimeters per hour. So if I integrate that, I'm going to get the total number of millimeters that that the radius has changed. So I'm going to go ahead and we're going to write that out the best we can. So for part A, I'm going to say it's the net change in the snowball's radius. Net change in the snowball's radius. Okay, measured in what? Measured in plain old millimeters from t equals 0 until t equals 24 hours. Okay, so that's a very complete and concise explanation that interprets the meaning of that integral. Okay, now as far as part B goes, setting up the left Riemann sum, I'm going to leave that up to you guys, all right? And I'm going to do setup only. Okay, so just make a note here. You're going to do setup only, and that'll be one of the things I'm looking for tomorrow in class as I do a brief check of your notebooks. I just want to see if we got the correct setup. I want to make sure we've got the correct length on our bases. I want to make sure we've got the correct heights. And then don't worry about crunching it out. I just want to see the setup. All right, let's move on to part C now. Change colors here. Now we want to use, again, using correct units, let's explain the meaning of this new integral. And the big difference, if you compare it to the one in part A, is now we've got this coefficient. And I want to ask myself, what impact does that coefficient have? Well, it's a beautiful coefficient because this matches up with our average value, or the average value formula that we saw the other night perfectly. If you're thinking, whoops, let's grab the pen. Okay. If you're thinking of 1 over b minus a integral from a to b of some, function, and that told you the average value of that function, it matches up really nice. This is like 1 over 24 minus 0, 0 to 24 of r of t. So what we're doing is we're finding the average rate in millimeters per hour that the length of the radius is changing. Now this one can be a little confusing, so I'm going to spend a little bit of time right here. But let's first of all get it written out. It is the average rate of change of the snowball's radius. Whoops, snowball's radius. All right, and that's measured in what? Measured in millimeters per hour, okay, over the interval t equals 0 until t equals 24 hours. All right. Now, why is that? Because, why did the coefficient of 1 over 24 totally change this problem? And, what happened to my units, really? So let's think about our units. We had, we had 1 over 24. We were integrating a function that was millimeters per hour. And when we got done integrating that sucker, we had just millimeters, right? But look at this. We were multiplying by 1 over 24. And what was the 24 measured in? It was measured in hours, wasn't it? And hours was in the denominator. So by the time I multiplied this guy times this number, I've got a new number that was truly millimeters per hour. So we kind of went full circle. We went right back to where we started. The bottom line is that when you use the average value formula, your units are the exact same as the original function that you started with. And I think that's worth putting an extra asterisk in your notebook and just mentioning that when we use this average value formula, the units in the end are the exact same as the original function we started with, just because of this coefficient bringing us back to where we started. All right, and one last thing before we abandon this problem. All right, I need you guys to do part D on your own as well. You're going to set up a midpoint Riemann sum. Don't forget about the coefficient. So it's going to be, you're going to have 1/24 out front, and then big square brackets. So I'm going to start you here. And then inside those square brackets, I want you to put your midpoint Riemann sum, okay, all the way across. And again, set up only on that one, and I'll check that for you. All right, now we're going to shift gears a little bit, and believe it or not, it feels like we're doing two totally separate different lessons tonight, but they are very closely associated with one another. I want to talk about displacement versus total distance traveled with regards to motion along a single line. So let's pretend there's our x-axis, and we have some random particle, and that particle is going to start here. I'll put S for starting point. Let's say he traveled, maybe 10 units this way. He stopped and he came back, let's say he came back 6 units. And then he stopped and he went forward, maybe 3 more units, and then stopped right there. And I'll put an F, that's my finishing point. So just to recap, the particle traveled 10 to the right, 6 to the left, and 3 more to the right. And I want to ask ourselves these two questions. What is the displacement? And what is the total distance traveled by this particular particle? Now, displacement is simply your finishing point minus your starting point. So I'm going to say that my starting point is only 7 units away from my finishing point, because I went out 10, I came back 6, so I was 4 units away. At this moment, if I would have stopped right here, my displacement would have been 4. But then I went 3 more to the right, so now I was 7 units away. So let's say displacement is 7 units, whether it's feet or inches or whatever. Now, total distance traveled, as you see, is a different animal. We're going to add the 10, the 6, and the 3 for a grand total of 19 units traveled. So displacement is always going to be, it can never be bigger than total distance traveled. It might be the same if he just traveled in one direction the whole time, but typically total distance traveled is a bigger number. All right, for this next one, I want to take a graphical approach in the sense, let's say they gave me a picture of velocity, and maybe velocity looked like this. And so we'll label this function. This is the velocity of a particle, and maybe the area there is 2, and that's t equals 3, and this is t equals 8, and that's t equals 12. And maybe the area of the second region is, I don't know, let's make a number, we'll say it's 10, and then this one's 7. So what did the particle do? He traveled 2 units to the right, and then he turned around at 3, and then he traveled 10 units to the left, and then he turned around at t equals 8, and he traveled 7 units to the right, and he came, we just stopped at t equals 12. So again, the question becomes, what was the particle's displacement during that time interval from 0 to 12, and what was his total distance traveled during the same time frame? So I'm going to say the displacement was really 2, let's see, get that 2 on there, there you go, minus 10 plus 7. We're taking into account that, whether we were going left or right, and I ended up with a total displacement of -1. And that's all you could think, well, I went, a grand total of 9 units to the right, 10 units to the left, so my displacement was -1. However, total distance traveled is truly going to be 2 plus 10 plus 7 for a grand total of 19 units traveled. So there's a big difference between the two. Now, how are we going to measure this algebraically? We've got 2 special formulas here. All right. In order to measure displacement, what we're going to do is we're just going to simply integrate the velocity function as it is. If certain parts are negative, aka below the x-axis, we're going to leave them negative. And that right there, that formula is going to be my displacement formula. Now, but if it's total distance traveled, the first thing I want to do is I want to force the velocity function to be positive. For instance, I wanted that 10 to be positive, so I'm going to force it above the x-axis, then I'm going to integrate it after that. Whoops, that's supposed to be t sub 2. So these are the 2 formulas we're going to start to use. Now, as we move forward here tonight, just to kind of speed things up, we're going to do our setups only, and then I'm going to trust that if we had to, we could evaluate the integrals by hand or on the calculator. Again, I just wanted to kind of recap our two formulas for displacement and total distance traveled, and we're going to go ahead and we're going to set these up. So for displacement in this particular particle, I'm going to integrate t squared minus 7t plus 10, simply the way it is, without any manipulations, interval from 1 to 7, and the number there would tell me the displacement. However, if I wanted distance traveled, I would use the same bounds, same function, but it would be the absolute values. So probably some of you are already thinking, if you take the absolute value of velocity, what do you have? Yeah, you've got speed. So basically, if you integrate the speed function, that's how you get total distance traveled. And I use the abbreviation TDT, total distance traveled. Again, nothing tricky here, very straightforward. They've given us these velocity functions. That's perfect. I'm going to say that my displacement is the integral from 0 to 5 of 12 minus 3t. That would be a great one to integrate. We'd find that one pretty easy. It's pretty straightforward. And the total distance traveled would now be the same bounds, but we would be using the absolute value of 12 minus 3t. And I always go back to that graph. I think thinking of that graph and the certain regions that were above and below really helped me convince me why I want the absolute values on this one but not the first one. And again, I think the second one, again, is very straightforward. I don't think we need to spend our time on another one. I think we've got it under control. All right, here's a great picture of a velocity function, and we're talking about, oh my gosh, I don't even know what that name is. Brina rides her bicycle from home to Sarah's house. So she starts at home and then she finishes at Sarah's house 15 minutes later, I believe. Yes, minutes it is. And this graph represents her velocity as she's riding her bike. So let's go ahead. I want to figure out the total distance traveled and the displacement. Actually, let's do displacement first, and then we'll do total distance traveled. And I want you guys to go ahead, try that on your own, hit the pause button, and calculate those two numbers on your own and see how we're feeling with this concept. All right, so I went ahead. The first thing I did was I calculated the individual areas of all the geometric shapes, and I said my displacement is simply going to be the integral of velocity. All right, sometimes we call it naked velocity just because it's on its own. Here, we're going from 0 to 15, and I'm just going to add up all the individual numbers, and let's see, 8.5, how about 17.5 for her displacement? And then for total distance traveled, now we're going to throw the absolute values on the velocity. We're going to dress it up, so to speak. And now I'm thinking, let's see, that's going to be about 23.5. Again, that number should be bigger. The best that displacement could ever do is equal. It'll never surpass total distance traveled. The next question I want to pose to you is there ever a moment where Brina turned around, so to speak, or did she just pedal straight to Sarah's house? And that question, we could say, is she turned around right at 4. It's almost like she forgot something and had to go home. And so then she, pedaled real fast, got home, and then when did she get home? Well, she got home at t equals 7, and then, turned back around and continued on her way to Sarah's house. So, and there's a lot of questions they could ask us about these, but we've accomplished the two things I set out to accomplish today. We got displacement, total distance traveled, talked about. So, hope that you're able to absorb the net change theorem, and we'll see you tomorrow.